Hello F-sharp, welcome back. This video is going to be a little different from the ones I have done in the past. Now I'm going to say up front, this is not a hot take, this is not me critiquing anybody, not at all. Something interesting happened and I wanted to dig into it and help us take away some engineering learnings from it. Now the thing that I'm referring to is Casey Muratori. Casey Muratori put out a video which is titled Clean Code, Horrible Performance. Now, I am a huge fan of Casey. I am actually enrolled in his class where this video is a part of it, and I think his class is fantastic. I'm learning a lot, and I'm an F-sharp developer, and so none of the code is written in F-sharp clearly, but the learnings are applicable to any language. So I saw this video right when it dropped because I got an email before any tweets went out, and I almost immediately went to Twitter and said, like, hey, check this out. This is fantastic. This is great. And there have been varied responses to this video, as is almost always true in the software development community. And my response is really going to kind of show my true colors. Now, I have said multiple times, I'm not really a software developer. No, that's not true. I would say I'm a software engineer. I am not a computer scientist at all. I started as a chemical engineer, became an industrial engineer, and wrote enough code that kind of got anointed or whatever and got turned into a developer. But I would definitely clarify that I'm a software engineer, started as an analyst, and that's why I fell in love with F-sharp. Because F-sharp is a fantastic language if you're an analyst. If you got sick of other languages being slow, that I will not mention, you want a language that's fast and feels like a dynamic language, but is statically typed and all the performance benefits that you get there. So I started kind of as an analyst, and I've kind of becoming more and more intense and more hardcore in terms of my concern for performance, because my whole thing is writing code to optimize supply chains, optimize and simulate supply chains, warehouses, and manufacturing facilities. That's really what I do. And so the code that I write has more in common with a video game engine than anything else. F-sharp just happens to be really great across a really broad spectrum of problems, which is why I like it so much, because I can turn to it when I feel like wearing my analyst hat, but it gives me enough tools to go as fast as I need to, all while having a clean, concise syntax. So for me, at the end of the day, all these things that they teach about how to write clean code and how to write correct code and all those abstractions, like, I really don't care. I care about solving clients' problems, and I care about code being maintainable, being readable, robust, fast. Like I care about all those things, but I don't have any particular love for any software development methodology. And so this is why I really resonate with the stuff that Casey's putting out, because he's really talking about, like, hey, how do we write fast code? How do we write good code? And like, what are the essential problems? And so in this video, he presented a problem from the kind of clean coding book, whatever it may be. And I'm going to say that that video, and I'm going to kind of show it right here, this clean code, horrible performance, and I'll have links in the description. Like, watching this video is pretty much going to be required to understand this one, because I'm going to kind of unpack what he did and show how to do it in an F-sharp way and look at the performance implications and how would we approach this from an F-sharp standpoint, and how would we make it fast from the F-sharp standpoint. So what he did is he presented this problem that, again, kind of comes from the clean coding resources. And it's the idea of, like, we want to abstract over some shapes. We want to iterate through them and perform a computation. In this case, it's the sum of the area divided by the number of corners plus 1. It's kind of a silly problem, but it's illustrative. And in the video, the approach that was taken from the kind of clean coding perspective, like, hey, if you're writing clean code, if you're writing good code, and again, I know that not everyone agrees with the tenets of the clean code or whatever that is. So I'm not saying this is everyone. I realize that the fsharp, the software development community is very, very diverse and very fragmented in a lot of different ways. But I'm just saying there is a school of thought. This is the correct way to do it, and there's a lot of people who believe in it. And this problem is saying, like, we have a shape, and the way to represent that is to have an abstract class. And so this is how I would write an abstract class in F#. And that abstract class has two members, area and corner count. And then I'm going to have several different child classes of it, circle, square, rectangle, and triangle, which all inherit from shape and provide overrides for those members. And then what I want to do is I want to say that, hey, I'm going to generate, in this case, what Casey, his benchmark was, is he had just over a million random shapes, and he had that in an array. And then the algorithm was to iterate through that and then compute something. And that benchmark is this. We're saying, hey, I'm going to iterate through all these shapes. I'm going to compute the area and then divide that by 1 plus the corner count. And this kind of covers the cases of a circles because it doesn't have corners and you don't want to be dividing by 0. And so for our data, to kind of replicate what he was doing, what we do is we say, like, okay, we have shape count, 1 through the shape count, and we're going to generate an evenly distributed set of shapes. And so I have an even number of circles, squares, rectangles, and triangles. And the reason I can put them all in the same array is because I've abstracted over them by saying, like, hey, these are all just instances of the shape abstract class. And so my benchmark then, as I said, is to iterate through all of them and to compute this sum. Now, Casey did this in C++, and I'm going to come back to the video. And this is the performance that he got with the completely naive version of it. So like the equivalent of what we have just done in .NET. And what the metric he was looking at is cycles per shape. So how many CPU cycles does it take to compute the area for each shape? And in the C++ code, he was getting 45 cycles per shape. Now, when we do that, we get the following number. We get 43. So for our total is 43 million cycles, but there's about a million shapes. And so on average, it's about 43 million cycles per shape. So this is great. It shows that, like, hey, apparently the .NET runtime is great. And .NET is just as fast as C++. You heard it here first. Just kidding. That is a joke. Yes, this is not a flame video. It's an engineering unpacking video. But the great thing is it shows, like, hey, .NET runtime just as fast as what was generated in C++. And so it's saying on average 43 million cycles per shape. Fantastic. Now, another approach that you might take to this problem, and let me like state Casey's point, and then we can kind of unpack that here in the .NET. Casey was saying in this video that following these principles of the clean principles, that he had 5 of them, and the first one is he said it as polymorphism. To be more specific, I think it's ad hoc polymorphism, because there are many different types of polymorphism. No, it's inheritance based in polymorphism. Sorry, not ad hoc. There are many forms of polymorphism. For example, parametric polymorphism is generics, right? And I think generics are fantastic. So polymorphism as an idea is not bad. There are particular types of polymorphism that I tend to veer away from. And we're about to get to one. Well, this is one that I would stay away from, and what's great about F# is it seriously de-emphasizes the idea of inheritance. You can do it. It's just not the way we typically think about these problems. So Casey's point with this video is he showed like, hey, I have these other versions which are more naive and more simple approaches. And he's showing like, hey, I get 4 cycles per shape or 3 cycles per shape, which is just massive, massive performance advantage over that. And he's saying, and part of what he was showing is that like when we just write code naively in this clean style, that there are massive performance implications. Okay, cool. What I'm interested in is kind of unpacking why. Why are there performance implications, and what can we then take away from that to inform how we write our code? Because clearly we can see it. When he implemented it with the kind of OO inheritance approach, it's 45 cycles per shape. And then when he had his simpler version, which we will show examples of in fsharp as well, he's getting 4 cycles per shape, 3 cycles per shape. And that is a 10 and 13x performance improvement by not using the object-oriented inheritance approach. So again, I want to unpack why, and we're going to get to that. But first, let's show some other approaches that you may take in fsharp. Well, in .NET, you might approach this using interfaces, which would be a very natural approach. So if we take an interface approach to this, we're saying like, hey, we're going to this interface is going to be the I shape, and we're going to have all these separate classes. We're going to have a circle class, square, rectangle, and triangle. And they're each going to implement that interface. And so then we're going to create our interface shapes. And what this is doing, I'm using the exact same data from the inheritance data set. I'm now just transforming it to instances of the interface version of this. So we're going to be, each of these benchmarks is iterating through the same data and getting the exact same result. But we're just kind of using different approaches to contain that data and iteration. So essentially the same thing. And when we go to the benchmark, we see the benchmark for the interface approach is essentially the same thing that we would see for the inheritance. Whereas, hey, for each shape in shapes, performance computation, add to the accumulator. Not that significantly different, but our approach to abstracting over the shape is different. Instead of inheritance, we're now using an interface. And when we do that, we see that the performance has gotten worse. We're now at 55 cycles per, approximately 55 cycles per shape. Again, because this is 55 million cycles to run the full benchmark, but we have approximately 1 million shapes. So I'm just dividing by 1 million to kind of get my number. So 55 million cycles per shape. It's worse. Yuck, what is going on? So let's talk a little bit about what the memory layout is going on in here. So in the inheritance version of this code, we had an array. And inside that array are our shapes. We're saying like, hey, this is an instance of the shape class. But what is that? What is that physically? Well, physically, since I ran this benchmark as in the 64-bit environment saying like, hey, target x64, these are references. So this is a reference to somewhere out on the heap. And in that heap, there is an instance of the class, right? And this is where things get a little murky for me. I am not deeply familiar with the internals of how the .NET runtime figures out like, hey, this class is an instance of this abstract class and it overrides this stuff. And the reason I don't know it is I don't use it because of the performance things that you're seeing. It's just like, it's slow. So why would I use it? And again, it kind of comes back from my background. Like I care about performance. And so I avoid things that are slow like this. And so there is some amount of information here that the CLR is using to figure out like, okay, it's an instance of this. It's an instance of this class. It implements shape using these methods. And so it works like that. Now, when we talk about interfaces, so if you have an interface approach, I believe this is what is happening. So what happens is, again, these are instances of an interface, but again, that is a reference to somewhere out on the heap. And now we have this I shape. And that I shape can then point to like, hey, this is the actual shape. So like circle or rectangle or something like that. In some scenarios, the runtime can de-virtualize this call. It can make it so like, hey, instead of having to go through all this work of having to go to the shape and then go to the actual instance of the class that we're wanting to work with, it can de-virtualize this because this is now a virtual call going through here. But it's not in this case. And so there's kind of two different levels of indirection going here. So I'm not surprised that the performance has gotten worse in this case. So interfaces, common way of abstracting over it. I actually put out a video earlier today where, actually it's yesterday and now it's after midnight, where I talked about like, hey, I am not against interfaces, but they do have serious performance implications. So in my hot code, I don't think I've ever used an interface because of this performance implication. It's not that interfaces are bad. It's just that they're not the right tool when you're needing to go fast. So be careful. And again, refer to that video if you care more about that. Now, another approach that we might take to this problem of kind of abstracting over these different shapes is to use a discriminated union. That would be the natural thing for us to do as F# developers. And so I wanted to check out what would that look like. And so when I do the DU version of this, I say like, hey, and again, I'm not profiling anything at this point. I'm just kind of using the different approaches and kind of emulating what Casey was doing. So Casey showed the idea of using inheritance. We've now done inheritance and interfaces, showing those are both very slow compared to what he was able to achieve. Now I'm going to use discriminated unions. And this would be what I would do if I just kind of went a little nuts. I wanted to define everything in here. So I have my type circle, which is just an F# record, and then square, rectangle, and triangle. And now shape is a discriminated union, which is how we abstract of like, yeah, I have a shape. It could be a circle, it could be a square, a rectangle, or a triangle. And then I can define my functions for working with shapes. And it's like, hey, if I want to compute the area of a shape, I would use a match with function, and then I would call the appropriate function for computing it. Same thing with corner count. So I've completely kind of abstracted the way, and this would be what I would call the natural F# approach to things without any regard to performance. And when I do this, what do I get? Well, I'm going to come back here to my benchmark, and now I'm at 51 cycles per shape. Not awesome. We are better than an interface, but we are worse than inheritance. Let's talk about why that might be. So when we want to know things about the F# memory layout is so critical for so many things. So I want to illustrate for you like what is actually going on here inside of here. So I have an array, and inside of this are discriminated unions. Discriminated unions and F# are reference types. And so each of these is, again, a reference to somewhere out on the heap. And what's even better is that this instance of DU, so I have my shape here. And what does shape have? Like, well, it has a tag field. This tag field is an integer, which indicates the different. Oh no, I have to double check exactly how this works. But if you'll notice, there's some mechanism here for saying like, oh well, which one is it? And if I come back to my code and scroll up, each of these cases has a reference to another record. So like if it's the circle case, it has a reference to the circle F# record. If it's a square case, it has a reference to the square F# record. Records are also reference types inside of F#. So this is going to have another reference to another thing. So this could be my circle over here, or some other shape. But the point is, this is holding a reference to another thing that is allocated on the heap. So again, we have these 2 layers of indirection here. That's how the memory is laid out in this case. That's less than ideal. So for each of these elements, we're going to be doing all these additional loads and lookups, and that can be spread out anywhere on the heap. So is that why our code is slow? Because again, Casey's able to achieve something far better than us. And again, I'm assuming you've watched Casey's video at this point. So what is going on? How can we speed this up? Well, before we get to alternative memory layouts, I want to point something out. We wrote our code in a style very similar to what Casey did for his benchmark. And so this is kind of our naive loop for the discriminated union. We're saying like, hey, we're going to iterate through all of our DU shapes, and then we're going to call DU shape area on our shape to compute the area, and then we're going to call this corner count on the shape to get the number of corners for that shape type. Now, something that you're maybe not noticing here is that the call to area and the call to corner count are both functions which have to match on the case of shape. Let's go ahead and go to them. So when I call area, I have to match on the case. And when I call corner count, I have to match on the case again. I'm duplicating work. I'm doing this match twice. And if I'm in a hot loop, having to look that up twice is expensive. So why am I doing that? So rather than doing that, let's instead kind of take advantage of the fact that like, hey, we want to look up what the case is only once and then utilize that information. And again, I'm going to use some of the techniques that Casey was using and saying like, hey, I know what these coefficients need to be. So I'm pre-computing the different coefficients for the different shapes. And so I'm not doing division anymore. I'm going to move to only multiplication, because multiplication of floats is faster than division in x86 CPU. And I am only going to match the case a single time, and I'm going to take advantage of that. So I don't have to do it twice, because I've taken advantage of that by kind of moving the corner count up into this coefficient calculation. So again, I'm just emulating some of the techniques that he was using. So I'm only matching once now. And so this is my kind of alternative DU loop. What's the implication of that? Well, when I do that, I'm now at 38 million cycles for a million shapes. So 38 cycles per shape. Better, but still a long way off from what Casey was able to achieve. Now, this is now one of the takeaways I want you to have is that it is critical when we are doing high performance work or we're wanting things to go fast. First of all, have a goal in mind. Have a finish line, because benchmarking and profiling can go on forever. It's one of those things that you can spend an infinite amount of time on. At the end of the day, you actually need to ship some code. So have a goal in mind and profile to figure out what you need to do to make things go faster. Don't guess. The next thing I'm going to show you is a guess approach. And then I'm going to show you why it's a terrible guess approach. And this is something that you might do naively if you don't know better, and something that I would do very naturally, like, oh, well, structs, right? Structs make everything faster. And it kind of makes sense when you say that, because when we look at what the diagram of this memory layout is, just like, well, a struct is going to inline this, so we're not going to have to pay this penalty of having these two lookups, right? So that'll make it better, right? Because this is what's slowing us down. Right? So, so let's do the structy approach. So I'm gonna say like my circle is an F# record, but now I'm gonna say no, it's a struct now. So now it's going to be a value type, and it's not going to be allocated on the heap automatically. Same thing with my square, same thing with a rectangle, same thing with triangle. And now I'm going to say, and my shape is a struct as well. And you would think like, okay, well, all this structiness, that's going to make things better, right? Because we're going to save ourselves from that indirection that we were paying for before. Well, if you were looking ahead, you probably saw that the struct DU approach was not better. In fact, it was worse, significantly worse. So 48 cycles per shape instead of 38 cycles per shape. Still, we're nowhere near where Casey was approaching, but we'll get to that. But I want to address why this is not helping, because it might be something that you would just you might think is be helpful, but because of some idiosyncrasies about F-sharp, it is not actually helpful. So we need to talk about that memory layout again. So how is a struct DU laid out in F-sharp? Oh, good question. Good question. So we got our array again, but it's struct DUs now. So what is actually in here? This is not a reference now. This is a struct. So we got our struct here. It has a tag field that you don't see, but is there, and it is an integer. And this is used to indicate the different cases. Now, something that's really important to know, the F-sharp struct discriminated union is not like the Rust discriminated union. The Rust discriminated union is fantastic because what it does is it looks at all the different cases of your DU and figures out what the largest one is and will only allocate enough memory in order to be able to store the largest possible payload in the discriminated union. That makes sense. F-sharp's struct DU does not work like that. I know it can't work with generics. It could possibly work with non-generic types, but I'm going to tell you how it works right now. I don't have the time to go into like the nuances of why. And I frankly don't know technically why. I just know how it actually works. What it does is it will allocate space separately for each possible space. Our shape has the potential to be a circle. It has the potential to be a square. It has the potential to be a rectangle, and it has the potential to be a triangle. Okay, how much space do each of these take up? The circle is 1 float 32. The square is 1 float 32. The rectangle is 2 float 32. And the triangle is 2 float 32. So each instance of our shape struct is going to be 4 bytes plus 4 bytes. Now we're at 8 bytes. Plus 4 is 12. Plus 4 is 16. Plus 4 again is 20. Plus 4 is 24. Plus 4 again is 28. So each of our shapes is 28 bytes. That is huge. It's like, and to be clear, like a single cache line for L1 cache is like 64 bytes. So like these things are monstrous, and they're likely going to be split across cache lines. Like this is no good. So this is why I actually very rarely use this kind of struct DU because of these implications. Now, like I said, that kind of explains like, oh, well, we're actually getting worse performance here. That's really bad. So again, you might naively think like, well, the way to solve that is to have a smaller discriminated union. And like, how do we encode that? And now we're actually going to use something that's kind of similar to what Casey was showing in some of his video, which is this idea of a compact DU. Now, I'm going to say up front, do not jump to this way of encoding discriminated unions. I do not recommend it. If I have done it, I only recommend it when you know you're dealing with an extraordinarily hot loop and those types are not leaking outside of your core library. Again, I do a lot of engine type work, and so a lot of my code like never gets seen by other people using the code. So I would not expose this externally. But what I'm doing is I'm saying, hey, every type has at least 2 measurements associated with it. Circle and square have a single measurement. Triangle and square have 2 measurements associated with it. So I can store all the necessary measurements for a given shape with just 2 float 32s. I'm going to have, in this case, an enum. It doesn't necessarily have to be an enum. A later thing I'm going to show requires it to be an enum, so I'll go ahead and make an enum right now. But in theory, right now, it could still be a discriminated union. And then what I do is I say like, hey, shape is now still a struct, but it has one field that is shape type, which in this case is this enum, but it could still be a discriminated union. And so this is an integer. This is 4 bytes. And it has a measures field. That measures field is a measures struct. And so this is 4 bytes, 4 bytes. So 8 bytes plus 4 bytes. So one of these is now 12 bytes. So less than half the size of the other discriminated union. And then when I want to work with it, I'm going to have to just show you the benchmark of how I work with this. Okay, and this is struct DU benchmark looked exactly the same. Compact DU. So I call this a compact DU, and it's the idea of like I'm trying to like keep the size of it very small, and I'm going to have to use the shape type to indicate which code to use. And so now what I'm doing is I'm switching on the shape type, and that tells me which version of this function that I need to use. Again, I do not recommend this, but this is kind of getting closer to kind of what Casey was doing in some of his video. But the idea is like, hey, maybe the problem we were dealing with is just like our types are too big, and so memory constraints was causing us problems. What if we took this approach? And again, we're kind of thrashing a little bit, but we're just like, oh, we just need to get the size down, and maybe that's the problem. And when we benchmark this using this approach, and this can be useful if you are in scenarios where you really don't want to be allocating, but you need a discriminated union, and so you want to struct DU, this is an approach you can take. Again, not recommended, not something I would jump to immediately or like secondly or thirdly. Like it has to be like, you need to have profiling and benchmarking proving to you that this is your problem and this is the thing that you need to fix. And I'm about to show you that it's probably not your problem later. But when we benchmark this, we get 32 cycles per shape. So better than inheritance, better than just a plain DU, but still nowhere near what Casey was able to achieve. And so just like, well, man, like F# is just slow. Please, we're not done. So I want to show you one of the things that Casey was doing, and we're going to try to emulate it. And I'm going to try to emulate it, and then I'm going to explain to you like why it's a good idea. So in here, one of the approaches that he uses is very clever and very commonly used in C level coding. And it's the idea of, I'm going to create a table of constants. And so now my computation, instead of having a switch statement to say like, oh, it's a circle, so run this code, or it's a rectangle, run this code, or it's a square, run this code, make it so that computation is the same for all the different shapes, and just look up the coefficient in this array based on the shape type. So the shape type is a union that's encoded as an int32. C basically has no rules. That's kind of a joke, but it's just like it's implicitly casting this union case to an int32 to look up the right coefficient in this table. So now instead of having a match with statement like you have an F# or some if then or some switch, it's just an array lookup. And this is basically encoding that switching logic by just indexing into the array to like a different coefficient. So this is clever. I'm going to show you how to do it in F#, and then I'm going to explain like why I wouldn't necessarily take that approach. So if I was to do something like that in F#, I would do something like this. So I'm still using the compact DU representation. It requires this. And what I do is I pre-compute all these different coefficients. I load them into an array that I'm going to do my lookups on. And then as I'm iterating through the shapes, I'm getting the shape type out, and then I'm turning that into an int. And this is a no-op. Like, this is completely free. Like, this is so you're not actually paying any performance penalty for doing any conversion here. And then I'm doing that lookup into the array. And so this is essentially the exact same logic that he was using. This was why I needed this to be an enum here. Before, the discriminated union approach is perfectly fine. Here, I'm needing to be able to just like immediately cast it to an int, and so I need it to be an enum. I don't like this, just from an F# style standpoint, because now I don't get the guarantees on like a match with statement that I have exhaustive checking. So again, this is more me trying to emulate the approach that Casey was taking, not something I would necessarily recommend. But what has happened is now, instead of having to have this kind of match with logic, these different if statements, we've now gone to like, hey, it's the same computation, and we've wrapped the logic of switching into like which coefficient we're multiplying by. And when we benchmark that, we've now gotten all the way down to approximately 5 cycles per shape. Not quite what he got to, I don't think. Let me double check. So he was here. So he's got 4 and 3 here. This 3 one doesn't count. Well, I mean, it does count, but he's using an additional technique to get more performance by like accumulating to several variables simultaneously to take advantage of the superscalar capabilities of the CPU. We're not taking advantage of it. So this 4.3 is really the one that we should be comparing to. So we didn't quite hit that, but we got really close. But we're starting at this point, like, I am not happy from a F# design standpoint. I'm not going to say it's wrong. And if you're in a high performance scenario where you have a critical benchmark that you need to hit, and you've done the profiling to prove that this is your problem, I'm okay with this. I'm telling you, I've run into it once. So it is incredibly rare. And now I want us to start to ingest an engineering lesson and think about, why did this give us so much better performance? Why? It's not just because it's clever. And the reason is in here. The reason is in this column right here. Branch mispredictions. You will see that we have huge numbers of branch mispredictions in our benchmarks. But when we went to this, hey, use a coefficients in an array and look up the index, our branch mispredictions went down 2 orders of magnitude, almost 3. That is the problem. So, and this kind of comes back to like how CPUs work. I have a video which talks about like memory hierarchies, but I don't have one. So I think I need to create one to really talk about how CPUs work. But like CPUs, like if you think about a CPU as a factory for data, it only has so much working space. That's the cache. And if the stuff it needs to work on is really far away, one of the huge performance penalties you can pay is having to retrieve something from memory. If something is like an L1 cache, you can immediately start working on it. But one of the other things the CPU tries to do, because it's aware of this problem with memory latency. What it will do is it will guess at which branch it needs to take to keep working, because it's going to wait on some other additional memory to load from like L3 cache or from main memory. And so what it does is like, okay, I have a branch. I don't know yet which way to go, so I'm going to guess so I can keep doing work. And CPUs are marvels of engineering, and they are incredibly good at guessing. But when they can't guess correctly, it is a huge penalty to the performance of our algorithms. And let's go back and look at our data. Our data is a uniformly distributed set of shapes across circles, squares, rectangles, and triangles. And so what's happening inside of our benchmarks is, and let's just go to just any one of these up here. So when it comes here, it's saying, hey, I'm going to try to match on this type. The CPU is constantly guessing which branch it needs to go on. Our data is uniformly distributed, which means it only has a 1 in 4 chance of guessing correctly. And when it guesses wrong, it has to throw away all the work that it did and then go back. It is a huge performance penalty. It's many, many, many cycles. So when we come down to this approach, why is this so much better? The reason it's better is because it's gotten rid of cycles. It's not better, like Casey's code was not better, faster because like it was in C, or he's taking advantage of stack alloc data or something like that. It's like, no, his algorithm was more predictable. That's what fundamentally changed. That's the important thing to take away from what he was doing. And I think that the question that we should ask ourselves is, what programming paradigms allow us to write predictable algorithms? What programming algorithms allow us to write small algorithms? Because small algorithms have a higher probability of fitting in cache, and therefore, if all the memory the CPU needs to work with fits in cache, it will run orders of magnitude faster. And so when we care about performance, we always want to be writing small code and predictable code. And so if a programming paradigm or some way of thinking causes us to write unpredictable code that takes up lots of space, it's going to run really poorly. And a lot of these techniques that we hear about for like writing fast .NET code, like the reason they work, the reason they are making things run faster is because it is compacting our data, our working set, the amount of data that we need to work with, and it's making our algorithms more predictable. That's what we need to be focusing on. Now, if you were able to write clean code in a predictable way, you could get just as good at performance. But I think one of the things that we don't, I'm trying to say how to say it. Like, so for me, like, that's what I want you to take away from this. Like, it's not that any particular programming paradigm is good or bad or anything like that. You need to ask yourself, like, what is it that you care about most? And if you care about performance, you need to be concerned about, is the paradigm that I'm using going to cause me to write algorithms that are conducive to being run well on a CPU? They should be small. They should be predictable. Now, my next idea comes from a couple of other people. And I want to mention them because they're great resources that I want you to check out. And I know this video is long. I warned you. So I want to go into the lineage of these. So there is a legendary talk by Mike Acton called Data-Oriented Design in C++. This talk is amazing. And he just, I've talked about this talk before, but I just put this one on like every few weeks just to like absorb it. And Mike is a much smarter, more experienced developer than I am. And I always really appreciate hearing from people who just have a whole lot more wisdom than I do. But he really kind of distills like what the essence of programming is. And again, this is where I kind of come back to the fact I'm a software engineer, not a computer scientist. I'm like, if software is transforming data at the end of the day, and it's all about data. And so he gave this great talk where he talked about data-oriented design and how to do it. And man, the comments afterwards, the Q&A session afterwards is epic. So definitely check this one out. It is a treat. But this then inspired another talk that is also fantastic by, oh my gosh, Andrew Kelley. Whew. Yeah. Oh yeah, right there. His name's right there. Andrew Kelley. So this is a talk that was given at Handmade Con, which is up in Seattle, and now there's going to be one over in Boston as well in 2021. And Andrew Kelley is he is the leader of the Zig programming language effort. I'm not sure what his exact title is, but he's brilliant. And Zig is a fascinating language that I'm also following, but he gave a talk which is kind of practical data-oriented design, where he was inspired by Mike Acton's talk, so inspired that you might recognize this T-shirt. So notice this T-shirt? Notice this T-shirt? Yeah. He got it specifically for this talk. It was hilarious. But he talked about applying these different ideas that Mike Acton was discussing in his talk. And this is, again, a fantastic talk. The link will be in the description. And so there's a thing that he mentions in here that inspired the next thing that I did. And he talked about like, hey, I'm dealing with scenarios where I need to know if something is dead or alive. And Mike Acton in his talk talked about the idea of using an entire byte to store a true or a false just like caused him so much rage, because that's basically 7 bits of data is like unused because you're only using 1 bit to store true or false. And so like, he's saying like Mike Acton saying like, don't do that. Andrew Kelley was like, yeah, but I need to know if something is dead or alive. Like, how do I encode that? And one of the things that he said was, oh, well, just keep those things in separate lists. If something is alive, keep it in the alive array. And if something is dead, keep it in the dead array. And now you're encoding the fact that something is dead or alive by where you put it. Encoding something by what it is, by like where you put it. And Mike also said in his talk that like code for the common case, code for the most common case. So when I ingest those ideas, what I end up doing is I end up doing the following, is I'm saying like, hey, I would propose this alternative idea. What if you're in the scenario where like, hey, I have circles, I have triangles, I have rectangles, and I have squares. And I have to deal with the fact that I have a collection of them. I have a group of them. And I don't know exactly what like the business case of this logic is. So like whether this technique is applicable or not, I don't know. But I'm telling you, this is something that I would try to use to see if it was usable in this situation. So again, I have my circle, I have my square, I have my rectangle, and I have my triangle. And now I have my shapes type. And my shapes type is saying like, you know what? I am not going to define a shape du. I'm going to say like, hey, I have this new collection type, which is shapes. And right now I'm just using an fsharp record. I would actually use something more sophisticated and has some validation around it. But the idea is like, I'm going to, if I want to have a collection of shapes, instead of wrapping each of them in a discriminated union or hiding them behind some interface or having them inherit from a abstract class, I'm going to say like, no, that's silly. Just store them in separate arrays. And then you know if it's a circle because it's in the circle array, or if it's a square, if it's the square array. But like, if I still want to be able to hold a collection of these shapes and pass around this collection of shapes, that's fine. I can still do that, but I'm not going to like hide what they are. I'm going to keep them separate. Now, this technique might not always be applicable, but like this should be on the table. And so this is me like creating my instance of shapes. I'm like, yeah, this is it. Like I'm going to take all those different inheritance types. I'm going to turn them into their actual concrete types and put them all in their own separate arrays. And now when I want to iterate to that, yes, this iteration has gotten more complex. I completely agree. That is true. If I wanted to, I could probably take some time to like make this like more sophisticated and elegant, but it is 1 a.m. here. So I got to wrap this so I can go to bed. But again, same type of loop, but now I'm just going to like, yeah, I'm just going to iterate through the circles and call the circle function, iterate through the squares. And like, yeah, if I have a new case, like I'm going to have to add some other things, but like, don't go through the trouble of wrapping these things in different shapes. And this might seem like an unexciting approach. Like, Matthew, that's kind of a dumb approach. Like, what if I'm just saying like, maybe this is the right thing for you. And if you really care about performance, like don't hide what something is, but you still can have a type for sharing a collection of them. Just keep them in separate arrays. And when we benchmark this, we get 3 cycles per shape. Massively faster. And so again, just because you're writing F# doesn't mean you have to write slow code. This also goes to show you why I generally do not use discriminated unions in my high performance loops. And it's not because DUs are bad. No. It's because branches are bad. And DUs, by their very nature, cause branching. So don't say like a particular tool is always bad or something like that. But be aware of, by using that paradigm, by using that tool, you are inherently injecting things that are antagonistic toward the CPU into your code, because you have to match on a DU, and that is going to create a branch. There's no way around that. Now, I didn't do something silly where what I could have done is like, hey, if I sorted the shapes in the array, maybe that would have been faster. It probably would have been. I should have run that. That would have been interesting. But what I'm seeing now is like, hey, the number of branch predictions is way, way down. And at the end of the day, like, yeah, I can still share a collection of shapes. I just keep them all separate. So, okay, we have gone super long. This is a super long video. This was really kind of fun. And I hope that you got some engineering takeaways from this. Don't take away that I'm saying like clean code is bad. I'm saying like paradigms which cause you to write code that is antagonistic to the CPU are bad for high performance scenarios. And some paradigms do that more than others. So thanks for spending some time with me. I hope you have a great day. Bye-bye.